Assalamu alaikum. Welcome everybody to the introductory course of AE221, the Introduction to Aerospace, and today we're going to be discussing Chapter 3, the Standard Atmosphere. So here in Standard Atmosphere, we are going to talk about four main key points, which is altitude, hydrostatic equation, standard atmosphere, and pressure, temperature, and density altitudes. So let's start by the question of why are we studying atmosphere? Basically, as an aerospace engineer, you are going to manufacture, or design a vehicle that is going to be flying through the atmosphere. So one of the steps of designing or making this vehicle is the understanding of the atmosphere that it is going to be flying in. So this is why the atmosphere is really important for an aerospace engineer. And as you can see here, the atmosphere consists of a couple of layers. And these layers are the turbosphere, stratosphere, mesosphere, thermosphere, and so on. Some say, or some countries say, that the end of the atmosphere, where the atmosphere ends and starts with the space, it's at an altitude of 100 kilometers. Others say it's 80 kilometers. So it's controversial. It's not important for us in this course for now. Let's move for the altitude. So altitude, there are 6 types of altitudes that you are going to study. First of which is geometric, then absolute and geopotential, and pressure, temperature, and density altitudes. So let's first demonstrate the first 2 versions. So here is our Earth. Let's say this is the center of the Earth, and this is our altitude that we want to reach. Okay, so the distance from the surface of the Earth until the altitude that we want is called the geometric altitude. And the distance, let's say this is the altitude, so the distance from the center of our Earth until the specified altitude, it's called absolute altitude. Okay, so also we have the Earth radius, r. So let's say we want to find the absolute altitude. So the absolute altitude, let's say, equals the radius of Earth plus the geometric altitude. And now we are finished with the altitudes. We need to emphasize also the importance of the gravitational law for the Newton, because we are going to use it later on. And now we are moving to the hydrostatic equation. So let's to try and simplify things for the hydrostatic equation, let's just assume that we have picked a column of air, or just a square of air, and it has some particles inside. So first, there are going to be pressure, there is going to be weight for the molecules, and so on. So first, let's specify our dimensions. We have 1 as the base, 1 by 1, and we have the difference in height, dHg. And here we have some forces, because here we have P, and here we have P plus the difference in pressure, because it's a very small column. So it will be the pressure, and then above it will be pressure plus a small difference in pressure. Also, they're going to be here in the center, the weight of the molecules. So let's just write the equation right here. Forgot to mention the equilibrium of forces. Forces acting from downward will be equal to the forces acting from upward. Okay, so P equals W plus P, which is this one here. This plus this will equal to this. So P plus dP. Okay, so here we will have to cancel these P's. So dP equals negative W. Okay, now let's go and solve this W, or try to derive W. So weight equals mg, and as we have mentioned before, mass, or M, equals rho multiply by volume. Density multiplied by volume. So what is our volume in this case? Our volume in this case is 1 by 1 by dH. So in this case, M will equal rho by 1 by 1 by dH till be only dHg. So let's write this again. So W, let's just change the color so we don't have any misunderstandings. So W equals rho G and dHg. Sorry, dHg. Okay, now let's plug this back in this equation. So let's just remove these writings. This will result in dP equals to negative rho G dHg. Okay, now that we have derived our hydrostatic equation, we move for the hydrostatic equation, but not the dH. We are going to use dH alone, because before we have used dHg because it is the geometric altitude, and here it is used the geopotential altitude. Anyhow, so we have dP equals negative rho G dHg. Okay, so we have these two equations. So now let's, as it says here, divide 3 by 2. This with this will give us only 1. And here the negative rho with the negative rho will be gone. Now dH over dHg, it is going to be the same. And G naught over G also will have this form. So going back to the Newton's law, G equals G naught multiplied by R over R plus Hg squared. Okay, now let's take this one with us down, drag it. Okay, now we want the form of G over G naught alone. So we have G over G naught equals R over R plus Hg whole squared. Okay, now let's memorize this one. Now we have been here, so we want the dH alone. So dH equals, we will flip these, so it's going to be G over G naught multiplied by dHg. And now we have this form, we can put this one in here. Okay, and this will give us this result right here. Okay, and if we integrate, so we move this differentials, till we will have this formula here. H equals R over R plus Hg multiplied by Hg. Okay, and that's it, yes. Now moving to the temperature distribution in the standard atmosphere. So these standard conditions that we have talked about the previous chapter are applied at 0 altitude. So these conditions apply right here. Okay, as we go or levitate through the atmosphere until we reach 11 kilometers here, we have a value of A, which is the decrease in temperature with altitude, of negative 6.5 Kelvin over kilometers. Okay, so through this region, this whole region, we have this value of A, which is the decrease in the temperature, and also and then we have this, I believe it's called a stratosphere, or yes, stratosphere, and then the turbosphere in this region. So in this region, we are going to have, let's just denote it in another color. We have a different value of A. So here the A is equal to 0, basically. Okay, so as you can see here, this is the value of A, and this is the value of the temperature at the altitude of 11 kilometers. And here we have the A equals the difference in temperature over the difference in height, which is also calculated here, negative 6.5 kilometers Kelvin per kilometers. And also we can solve simultaneously by just substituting for dH. So dH equals dt over A. And this we will substitute in equations 7 here. But first, let's just discuss these equations first. So in the first 11 kilometers range, we are going to use these equations, basically, where ρ1, P1, and T1 are the values of these standard conditions. Okay, so either it's going to be given the pressure and we want to find the temperature, or the opposite, and we also have the pressure, density and temperature. And as we've discussed before, if we are giving one, we find the other one. And also we have here the temperature at a specific altitude. And what else we have? These are the values for the standard conditions in the American system or the English system. So basically we have temperature, density, and pressure. If we are giving the temperature, find the pressure. If we are given the density, find the temperature. If we don't have neither the temperature or the density, we use this first, find the temperature, and then solve for the density. This is for the altitude from 0 to 11 kilometers. And if we go higher than that, from 11 kilometers to 25 kilometers, we have another equations, because there is no A, as you can see here, it is going to be 0. And also just a reminder, the value of R here is 287.05, if I reckon. So here are the conditions for the altitude from 11 to 25 kilometers. We have another equations. This equation that relates pressure to the height, and also here the density. So we've talked before for the P1, okay, from 0 to 11, and it is specified as the standard conditions. But in this case, how can we find the P1? So first of all, we need to solve for the P1 from P1 here from these equations. So we put the altitude here to 11 kilometers and then solve simultaneously for these equations to either get the pressure or the density, and then use them for P1 or ρ1 in this equations to get the P at specific altitude ranging from 11 to 25 kilometers. So at the end, there are at the end of the book, there are going to be some appendix, A for the metric, I believe, and B for the English units. Just go through them. I think they are not that important, but you can use them to solve some exercises in the book. And thank you for listening. I hope you enjoyed that. And if any questions, you can ask either in the comments or the group. And we will have another video solving some equations regarding this chapter, inshallah. Thank you.